All right, this video is about applications of estimating with finite sums. So we've already done that a bit, and now we're going to do a couple just quick little reviews. So this is a chart that is showing us the velocity of our car. We're driving along a road, and we're taking note of our velocity every 10 seconds for 60 seconds. We're wondering how far we've traveled in a minute. Now, we can approximate that distance by using different strategies. So, for example, if we use LRAM, LRAM says that we're going to make rectangles where the left corner of our rectangles are going to touch the curve of our velocity function. So that means that for each rectangle, I'm going to multiply by the width of the rectangle. The width of my rectangle is going to be based on the change in time. Now, fortunately for us, the change in time every interval here is 10 seconds. So actually, I factored this out. This represents 10 seconds. Okay, it's going to be multiplied by, and so now I could distribute this 10, each one gets multiplied by 10, so now I'm just going to multiply by the velocities that we have, but because I'm using LRAM, I'm going to choose the velocities on the left. So I'm using 0, 44, and so on, all the way up to 44. Notice I do not use 35, because if that was my last rectangle under the curve, then 44 is going to be the one that is used. In other words, the left side of that rectangle, okay? And so then I can multiply those through and I can see that I get 1,680 feet. Remember, units can help us think about this too. My time here is 10 seconds, is it measured in seconds, and it's being multiplied by feet per second. That's what we've multiplied. Each of these velocities are measured in feet per second. When you multiply those out, that gets you feet. So that helps us to understand why when we are looking for the total distance traveled or distance traveled, we are multiplying our velocity times the time. Okay? If I was going to do the same exact chart but use RRAM, again, the 10 is representing the intervals of the time because they are all equal. I can multiply it out on the outside, factor it out on the outside, so this is in seconds. And now the only difference is that my velocities that I'm using here that are measured in feet per second are starting with the first velocity that is on the right side of the first rectangle. So if this was a rectangle, I'm no longer using 0. I'm using the velocity that would be on the right of this rectangle, which is 44. And that means I go all the way up, and I do include 35 this time because that would be on the right side of that rectangle. And so I can see that my approximations are pretty different. Using RRAM, I'm estimating that I went 2,030 feet, and using LRAM, I'm estimating that I went 1,680 feet. And those are differences that, depending on the results, can be significant depending on the estimation technique we use. Okay, so now we're going to use this to do something a little different. We've been estimating the area under a curve, right? So multiplying by the areas of those, to create the areas of those rectangles that we are approximating, then adding them up. But you can do the same thing to approximate volume, and that's going to be something we're going to be doing much later, much more frequently later on, but we're going to start with the approximation. So let's say I had this blue line here on this blue curve that is represented by y equals square root of 16 minus x squared. And what's happening is that we're taking this curve and we are rotating it around the x-axis all the way back around. I've inserted this picture just because to me it always makes me think of a decoration like this, where I imagine that I'm taking one of these curves that goes from here to the other side, and if you rotate it around, you're creating in its wake sort of this three-dimensional sphere. So this is creating a sphere, okay, by revolving this function around the x-axis. Okay, now to approximate its volume, we're going to do the same thing we did up above, which is we're going to slice it into pieces, but now those pieces have to be three-dimensional, and we can imagine that one way that would be useful to do this is to slice it into cylinders or discs. Okay, and so we decided to slice it into 8 subintervals, and so we're going to be creating 8 cylinders, and we're going to add up their volumes to see what their approximations would be. Now notice that these are cylinders that are on their sides, right? Often we think of a cylinder like this, right? Its height would be this distance, its radius would be this distance here, right? But this cylinder here is on its side like this. Okay, so its height is this distance right here, so that's what I'm marking here in green. The height is representing these distances here. And because we cut it into 8 equal subintervals, those distances h are all going to be the same. Because this function here goes from x equals -4 to x equals +4, I can see the height of each one of my cylinders is going to have a unit of 1. Okay? The other thing that's important for us to remind ourselves is that if we are looking at the volume of a cylinder, sorry, I'm skipping around here. The volume of a cylinder is pi r squared times h. So what do I need to find the volume of each one of these slices? I need to find their radius and their height. Now their height, we just said, is going to be constant. So that's going to be a 1 in this particular case. It could vary in other cases, but here it's going to be constant. But I hope what you can see in this picture is that the radius is not going to be constant. The radius of this cylinder is this short distance here, whereas the radius of this one here in the middle is a much bigger distance, which is right here. So that's going to be a function, right? It's going to change depending on where you are looking. In fact, it's going to change as a function of x. Okay, so r is actually going to be this vertical distance here. How do you get a vertical distance on an xy plane? You do the y value on the top minus the y value on the bottom. Well, the y value on the bottom is always going to be 0 because it's around this x-axis. So if I did my y value on the top, my y value on the top is square root of 16 minus x squared. So r, what's going to go in here, is going to be the square root of 16 minus x squared, which will in fact vary by whatever your x is. So let's go down to our chart where we're going to be approximating our volume. So notice that I made this chart. I'm breaking up into subintervals from -4 to 3, so on and so forth. Okay. The height of my cylinder, as we said, is going to be 1 for all of these points. Okay. The radius of the cylinder. So this is using the left endpoint. So it's similar to saying I'm going to use LRAM. My left endpoint of this first subinterval is -4. So we said the radius is going to be the function here. As I said here, radius is going to be the function that we were rotating, square root of 16 minus x squared. So that's my radius, square root of 16 minus, and I plug in for x the left endpoint, which in this case is -4. Now it turns out that this one is 0, meaning I don't even have a cylinder if I use that left endpoint. It has a volume of 0. Okay, go on to the next one. My height is going to be 1. Again, that's constant for all of these. And now my radius is still going to be the square root of 16 minus x squared, but now my x is going to be the left endpoint, which is -3. So if my r is square root of 7 and my h is 1, because volume is equal to pi r squared h, if I square the square root of 7, I get 7 times pi times 1. That's where I'm getting 7 pi from. Okay, and you can pause this video and go through a couple of these examples. Hopefully it will make sense to you. If you add all of these volumes up, this is saying that your approximate volume of the sphere using the left endpoint as your estimator is going to be 263.894. Okay, again, I'm going to let you pause the video at this point. Do the same thing using the right endpoints. Notice that what happens is now in this first interval, you do have a positive volume, and in the last interval, you have a volume equal to 0. And you should see a lot of the same numbers because if we go back to the image of what we're looking at, this is symmetric, right? So for every disk that's on the left, you expect to see the same volume of a disk on the right, okay? Also interesting for us to see is that the actual volume of a sphere, which can be calculated with the formula for the volume of a sphere, 4/3 pi r cubed. If I plug that in with a radius of 4, which is what the overall radius of this sphere would be, then I would get 268.083. So I'm using 4 as my radius because this distance here from the center to the edge is going to be 4 in this particular case. Okay, so we can see that these estimates are a little bit low, but they do work. Again, you can pause the video here to take a look at approximating the volume using the midpoint, and you'll see that that gets you a little closer to what the actual volume would in fact be. Okay, these would be in units cubed, whatever these units would be.